Thanks for joining me and coming back from lunch soon. I know there's not a lot of time. So I'm Ian Bennett. I'm a software engineer on Twitter's observability team. I think it's worth mentioning how great all of the other speakers have been during this conference, and give everybody a round of applause that's set this up. This has been awesome. And if you're like me, you've probably been soaking up all of the talks like a sponge, and at this point, your brain is probably nearing capacity. So try to make this a little bit of fun. Hopefully this is interesting. And the title of this talk is Critical to COM, Debugging Distributed Systems. I think this week has sort of been described as critical to COM with the power outages and all the other crazy stuff that's going on. I think today is a pretty chill day. So that's what we're going to talk about. We're going to talk about some of the experiences that I've had since joining Twitter's observability team, some of the stuff that's resulted in us getting paged, and not knowing necessarily what the next steps were. There wasn't a clear way to resolve those issues. And to set some context, our team's objective is to allow engineers to gain insights into and optimize their services in real time. From metrics collection and querying to alerting and visualization. We deal with an interesting scale problem in that we're currently handling over 3 billion unique metric writes per minute. And that was at one time up around 4.3 billion. So let's dive into this. We're going to start off with a case study, and this is called Diving Instances, and it's a simple fix. So we've got the stateless service that's running in Aurora. If you're not familiar, Aurora is a Mesos framework for long-running services and cron jobs. We looked at our service dashboards, and it was telling us that the host uptime was averaging less than an hour. This was due to high garbage collection overhead, and Aurora was failing the health checks due to these long GC pauses. So what we did was we attached a profiler to an instance, we took some CPU samples, and that told us, if you have never seen YourKit, this is a YourKit screenshot. I'm a big fan if you're using the JVM for a profiler. And this stack trace here is just determining the hash bucket for a Scala hash try map key. So why is that a problem? And what can we do to solve it? If you're not familiar with Scala, the concept of a case class is different from a standard class in that it auto-generates some things for you and exposes some handy language features like being able to decompose things through pattern matching. The caveats to that are that we were using this case class as the key to the map. And Scala's case class auto-generates a hash code for you. If you've ever done that over collections, what ends up happening is it hashes over every element in every collection in the fields that you define within that case class. So this was going through all of the collections that were defined as fields and burning up CPU and causing tons of GC. And we provided a custom hash code, deployed that, measured and validated that it was fixed. So if you look at this, you can see all of these hosts just falling over, and then we deploy the fix, and they're up more consistently. And this is over the course of a little over a month. Some of those that are still falling over is stuff that we're working on right now. So since we got through a quick case study, I'll go through the methodology that I like to use to solve these problems. So the first thing to do is to measure something, because if you can't measure something, you can't quantify it, and you don't know if you're actually impacting it when you make changes. So first measure, then analyze the results of that measurement, make an adjustment, and then verify that the adjustment that you made is pushing you towards the goal that you want. And I have a background in performance optimization. I like to use the term peeling the onion when you're trying to dig into problems. So this is what I like to consider the onion of determining how to continue to move forward with solving these issues. So the outer layer of the onion, you start outside and work in. The outer layer of the onion is metrics, and for us at Twitter, those things are dashboards and Viz and our Mon 2.0 service where we have monitoring and alerting set up. Once you understand the metrics, you get to the point of trying to do tuning. Tuning is cheap. Tuning are things like changing application parameters, JVM settings like your heap settings and garbage collection, the style of garbage collection that you're using, your container settings, whether you're changing CPU allocations or memory settings, and then operating system kernel level tunings you can get into. If those things are cheap and easy, do those. Once you get past that point where you can't fix it, move down to tracing and logs. And in Twitter, we use Zipkin for our distributed services tracing, and we use Loglens for our log aggregation, which is pretty similar to Logstash. I'm sure most of you have used that. On the profiling side, these are low-level OS tools or JVM profilers like that URKit snapshot that I showed you. And then if you can't figure out what you're doing from a profiling perspective, if there's not enough visibility into that, you get into custom instrumentation or code changes. And typically, like profiling, if you find the issue, you're probably gonna have to make a code change in order to resolve it. So they sort of work hand in hand. And based on the fact that the other speakers have done such a great job of going through the top 3 layers of this onion, I'm gonna spend a little bit more time talking about profiling, custom instrumentation, or code change. So this is when to peel the onion. So we've got this methodology and we've got the onion, so we understand these layers and what to do. The concept is that you should make a single change at your current layer and continue to repeat the process of looking through this information and trying to move towards a target. You want to avoid the urge to make too many changes at once, and I know I've done this a few times where I'll go through and I take a profile and I say, these are the top 3 things that are wrong. Let me go and change all of those 3 things. It's a really bad practice to get into, and it's going to cause you a lot of trouble. So you need to be able to measure the positive and negative impact of that single change that you're making and verify that you also haven't changed the behavior of your system, that your fix was something that actually improved performance and didn't break your functionality. And then you also need to remember to re-rank and prioritize, because you could uncover bottlenecks that you didn't see the last time you took measurements, and you may not have enough information to actually make that next change. So at that point, that's when you peel to the next layer of the onion. So talking about profiling for a second, these things make up your performance. CPU, memory, and I/O sort of battle each other to determine what your application is going to be able to output. From a CPU perspective, profiling would be like looking at CPU samples, stack traces, doing tracing profiling, doing lock weight analysis. From the memory side, this for Java would be static heap analysis or like garbage allocation. And then on the I/O side, this is network and disk. And Julia's talk was much better intro at these things than I'd be able to give in this amount of time. So luckily I don't have to do that now, and I can skip into a little bit more complicated stuff. So that was profiling for a single thing, and now we're looking at it from a distributed perspective where all of these little things, these funnels are your service instances. So as Ben showed yesterday, you want to look at the worst offenders and figure out where those things are. Zipkin should be pretty decent at figuring out what part of your service is causing the largest problem. And basically we're just trying to isolate out bad actors and look at that one first. And that would be that one. So this is the one place that should get the most of our attention until that's not the largest offender anymore. So common issues that I see are things to do with logging, and this is people not understanding our logging framework. I'll get into that a little bit more in a minute. On the Java side, this is auto boxing. This is things like using collections or maps that contain primitive types. They have to be boxed. For an example, this would be integer versus lowercase int. There are caching and memoization issues, which you'll see some of that too. Concurrency issues, which you'll also see some of, and expensive RPC calls. And this is things like thrift messages that are using structures that are inefficient for what you're trying to do, and then they cause an impact not only over your network, but they're going to cause an impact on your application too, because you have to deal with serializing, deserializing, all those things. So quick performance pro tip, if you do go into making performance optimizations, keep your code abstraction sane. Your performance fixes should be as isolated as possible, and you don't want to expose those pain points to your customers. The reason why. Your bitmap exclusive or bit shifting super efficient string deduplicating object pooling concurrent set is awesome, but your consumers shouldn't need to know like the underlying algorithm for that thing, and exposing that to them is just going to make things worse. This code becomes very brittle and hard to work around. Reason for this is that your micro optimization can also become obsolete. There are things like new library comes out, and that performance optimization, if it didn't make it upstream in this open source library that you're using, someone else did something better. Now you have to make all those changes in all these different places. You got compiler improvements that, for example, if you're using the multiply sign versus bit shifting, if the compiler optimizes that, it might actually be faster to go back to using the multiply sign versus doing bit shifts if you're trying to micro-optimize that. And then usage patterns for the application change, so what you spend a lot of time doing there, you're gonna have to do it again. The other problem with that is uncaught bugs. You might not realize something even if you have passing tests and you've got something deployed out into production and it's working great for a while, and then you realize that there's some functional issue that was caused by your performance change. You're going to have to make changes in all those places again too. Great. So fire, you've got critical issues, your pager's going off constantly. So what to do there? Stick to the methodology that I listed out. Don't panic, don't create more problems by skipping steps or guessing. Your gut can and will be wrong about the thing that you want to change. You're probably going to be tired, especially if you're getting paged at 3 or 4 in the morning. You're going to be frustrated because who wants to deal with pager duty alerts going off anyway? And you need to spend days iterating on changes to remove bottlenecks. Like, this might be something that takes weeks. So having a methodology where you're tired, you're gonna have to work through this stuff, it's just gonna save you pain. So let it guide you to a solution and reduce stress. So we're gonna look at another case study. This one is heavy garbage collection, and we can't tune our way out of this one. So we've got this stateless service that's running on bare metal. It's got high CPU, excessive GC, and low throughput. We attached a profiler to the service, and we enabled some object allocation recording, and we saw that string format calls were causing excessive allocations. So let's look under the covers at what string format does on the JVM. Okay, so this is just defining some metric names, and we've got Manhattan frontend app ID, %s reads, and all we really want to do is replace what that %s is, because we have like a couple different things that we're tracking with our metrics. This is a pretty bad pattern for metrics collection in general, but it's necessary in this case. So what's happening here is they're trying to create or get this metric if it's already been created, and then we're doing a string format call with that format, and we're passing in whatever that thing is that's supposed to be replaced. That's the fully qualified metric ID. So this is pretty bad if you look at this. Basically what's happening is that under the covers for string format, every time that format is called, it's compiling a regular expression, doing pattern matching just to replace that one value. And if anybody's worked with the JVM or practically any language, if you're dealing with regular expressions, it's going to be extremely expensive. So the solution to this is to change this so that we're not using regexes. We can just concatenate the string when necessary. We know the things that make up the metric ID that we're trying to use, and all we're doing is going to a cache and passing in the contents of what would make up that metric ID. If it's not in the cache, we concatenate it. Otherwise, we get it, and then we increment the metric. So that helped, but it didn't fix the issue that we were seeing. Performance issue wasn't resolved, and there was something else that was lurking behind the string format. I had to remove some of this for legal reasons. So that's my cat, one of my cats. So don't mind any of that. Underneath is what's important. This request stats initialization is happening tons and tons of times. And this is eagerly initializing a bunch of collections. So analyzing that code found that the many sub-collections that were being eagerly initialized weren't actually part of like the typical request response sequence. It was only a small fraction of them that were actually used during one of those. So the solution to this was to lazy initialize them instead and basically use immutable empty collections that the other code that exists that depended on the stuff didn't break. And then only on the first mutation did we actually initialize that collection. And then applying the two fixes for the string format and the lazy initialization actually increased the capacity of our distributed key value store significantly, which is good because our observability stack runs on top of that. So this is going to be another fun one. Iterating on this, we're looking at logging. Know your logger. So this is a method that's got a log trace, and we've got some string. We talked about string format, and there's some other stuff going on. Does anyone in the crowd want to take a guess, like what's wrong with this? No?
It'll always format it even if you're like not actually going to the trace level.
This is true. And what's extra wrong with that is we have no idea what entity and at.toString, how expensive those things are. At was actually like a massive collection, and it required going over the collection to generate the toString. So every time we were hitting this method, it was just exploding memory to do a trace call that the logger was going to ignore because trace isn't turned on in production. And apparently it removed one of my slides. So know your logging framework. Yeah, the fix to that is to not do that. Essentially, remove the format, there's a comma, use entity, and don't do toString unless you need to. Let your logging framework take care of that for you. Okay. So we're going to get into this crazy case study. And as a side note, Jan, who was the previous speaker, actually worked on the service that I was talking about here. And we talked about it a little bit at the speaker's dinner, and he apologized profusely for this code. But Jan, this isn't your fault. The code that I'm going to share doesn't have to do with what he did, and even if it did, it's a blameless postmortem. So, Nuthatch is our temporal indexing service, and the logging fix that we just went over was actually part of trying to debug an issue with this service. The success rate was plummeting between 9 a.m. and 5 p.m. Pacific time, except during the lunch hour. So this is a little bit strange. And this is a chart of our success rate, and you can see this actually took us days to debug this issue. And you can see at lunchtime, success rate goes back up, which is really strange. Why is this happening? So in order to solve this, we have to use our toolbox. We have dashboards. They show us that GC spirals are out of control. Our system memory usage is nearing 100%. These are static hosts. This is a stateful service because it's an indexing service. We can't increase our heat because we don't have any memory to. And we can't do some tuning that would easily resolve this. So we narrowed down some specific hosts with the worst case issues. We pulled logs. There wasn't enough information in logs. We attached a profiler. We pinpointed some code using CPU profiling and allocation profiling. We even took some heap dumps and compared some snapshots. We put numerous fixes in some canary instances to try to see if this would help us with our issue, but it wasn't enough. So we need more context. Like I said, Zipkin, it can point you to the thing that's having an issue, but it doesn't tell you anything about what's going on inside that thing. Context is really important. And the logging that we had there also needed to be bolstered because there wasn't enough information in the logs for us to determine what was happening. And if any of you have ever used Finagle, which is part of the Twitter stack, I really like the concept behind it because it tries to make you treat your service as a function. and you have the ability to just easily create filters in front of your service to do filtery things. So what we did was we created a low overhead filter that tracked the top N worst offenders. And we were able to inject some context into that, like what was the request that was coming into the service, how long did this thing take, what were the other requests during this time period. We opened up an HTTP endpoint, and so we were able to connect to that endpoint and grab these stats as necessary and just let them accumulate over time. And we found the culprit. And when we applied the fix, our success rate went back up to about 100% pretty consistently. And before that, we were at 800,000 failures per hour that were going through our index service, and then back down to 0. So the fun part about this is what was actually causing the issue. So we had this stateless service that was increasing its number of instances and its number of metrics. And these things were being indexed, which is fine. For the most part, that wouldn't cause any issues. One developer had their dashboard open on their desktop. And this dashboard had a regex match against some metrics. They hadn't changed anything. We hadn't deployed a new instance of the service in a long time. There was nothing that had changed from a code perspective. Just more instances, more metrics, more expensive lookups. So our solution was, since we've added in this instrumentation, we figured out which service it was that was responsible. We went down to the developer's desk and we asked them if they could close this dashboard for a few minutes while we watched our success rate. And it went back up to 100% when they closed their dashboard. So this isn't really an acceptable solution, and something else was wrong. The code was reviewed and tested. We actually had a cache in place that improved things in the past, and this really shouldn't have been an issue. This shouldn't have been a performance problem. This should never have caused any customer impact. So this is some code that we had in that service. And what this is doing is a cache lookup. And we've mentioned that observability and having metrics to track your application is a great thing to do. So that's what's happening here, is we're going to the cache, and if something is in the cache, we're incrementing a hit counter and we're returning that value. Otherwise, we're incrementing the miss counter, we're going to the service to do this expensive operation. If it has an empty result, we're incrementing a counter. We're putting that thing in the cache, and then we're returning the results. So that call right there to the service before it puts the thing in the cache, it's not a blocking request. So that's actually like this, where you have tons and tons of GET requests that are coming in. They're looking up the same key, and all of these things are processing and processing and processing. So the first insert would actually happen at that gray line. So the first get that actually pulls out of the cache is at the bottom of that gray line. And this was causing the GC spirals. It had just gotten so out of control that the processing in the cache never got to the point where it could catch up to this thing that was going on. So the solution is to just go to the cache for everything and deal with incrementing counters and stuff on the cache object itself. All of this stuff is non-blocking, and it does the same thing. So that looks sort of like this, where everything is going, grabbing that value, and it's waiting until it's available. So we rolled out that fix, and you can see here, we were sitting pretty close to 100% memory until that was rolled out, and then we got 30% more headroom, and the service has been stable since. So we were pretty calm and able to sleep then. So now that we're in a happy place, it's a moment for us to reflect on some of the stuff that I went over here. What can we do to make each other's lives easier going forward and help each other not cause these issues? So we should be able to gain some insights from looking at each of the layers of the onion that I had shown you. And these things should allow for discovery, right? We've got dashboards and we have metrics, we've got logs. All of these things aren't really connected to each other, and there's a lot of contextual information that's lost. And a lot of the speakers this week have been talking about this. This is something where, like in an ideal solution, we should be able to go from the outer layer of that onion to the inner layer of that onion and back out and be able to see insights into what our applications are actually doing and what the health of our services is in long term. And this is a pretty wide open area. And I think if you're interested in this sort of thing, you should probably come work with me at Twitter because I'd love to spend more time working on this. So yeah, there are a couple other things. If you have any questions about this, if you want to talk about profilers or any other like metricsy related things, feel free to reach out to me on my Slack channel or Twitter. If you go on my Twitter, I'm going to do something else right now. I think it's been great that you guys came in here for this talk. But what I'm going to do is I'm going to post out this poll, and I'm interested in seeing your input on this. A lot of the stuff that's been talked about this week are things that we have sort of solved at scale at Twitter already, and we're just holding on to them. So I'm interested if you guys would like for us to potentially open source our observability stack or offer it as a hosted solution or open source and host, or just keep it to ourselves because you don't care. So I'm posting this right now, and you guys could feel free to give your feedback on that, and thank you for everything.